Hello. In second chapter, we are taking the next theorem today. First, we see two definitions. Dual space of norm-linear space capital X. Let X be a norm-linear space and X dash its dual. If there is a norm-linear space Y and the linear operator T such that T is a function from X dash to Y, which is 1, 1 and on 2, and norm of TF is equal to norm of F. All of F belongs to capital X. F is a functional. F belongs to X dash. Here it is X dash. F is a functional. Dual space of norm-linear space. Let X be a norm-linear space, then the set of all bounded linear functionals on X constitute a norm-linear space with norm defined by norm of F is equal to supremum over X belongs to domain of T, norm of X not equal to 0 of mod of F of X upon norm of X. Set of all bounded linear functionals on X is a norm-linear space which is called as dual space of X. After this definition, we see this definition. Dual of norm-linear space X. Let X be a norm-linear space and X dash is its dual if there is a norm-linear space Y and the linear operator T such that T from X dash to Y is 1, 1 and on 2, and it preserves the norm, that is norm of TF is equal to norm of F. Then Y is called as dual of X. Here one line to write. Y is called as dual of X. We have taken X dash as dual of X, and there is a mapping T from X dash to Y which is 1, 1 onto an isomorphism. That is, it preserves the norm. Hence, Y is dual of X. L1 space, it is a set of all sequences such that summation I is equal to 1 to infinity mod of xi less than infinity, xi to the power 1, because it is L1 space. Xi belongs to scalar field. L infinity space is a set of all bounded sequences. An isomorphism of a norm-linear space X to Y is bijective linear operator T which preserve the norm, that is norm of Tx is equal to norm of X. And we say that X is isomorphic with Y, isomorphic to Y. And T is isomorphism. Next, theorem. Prove that dual space of L1 is L infinity space. Proof. Let L1 is equal to set of all sequences alpha I. I is equal to 1 to infinity. Alpha I belongs to scalar field K. Summation mod of alpha I less than infinity. is a norm-linear space with the norm of alpha I is equal to 1 to infinity is equal to summation I is equal to 1 to infinity mod of alpha I. K is generally set of all real numbers. Let L1 has a shorter basis or only basis, say E1, E2 up to so on En. Then EI is a sequence. Each EI that is E1, E2, this is a sequence whose ith term is 1 and all other terms are 0. Here norm of EI is equal to 1. This is from the step where we have defined the norm on L1 space. For any x belongs to L1, this is L1. X is equal to summation I is equal to 1 to infinity alpha EI. For any x belongs to L1, x is equal to summation I is equal to 1 to infinity alpha EI. Give this equation number 1. X is expressed as the linear combination of elements in the basis of L1. X belongs to L1. Let F belongs to L1 dash, where L1 dash is dual of L1. It contains bounded linear functionals. And F is a functional from L1 to K, is bounded and linear. That is f of x is equal to f of summation I is equal to 1 to infinity alpha EI is equal to summation I is equal to 1 to infinity f of alpha EI. We define f of EI is equal to lambda I, where lambda I belongs to K. So that is equal to summation I is equal to 1 to infinity alpha into lambda I, because f of EI are lambda I. Give this equation number 2. Now, mod of lambda I is equal to mod of f of EI less than or equal to norm of f into norm of EI, because f is a bounded linear functional. F belongs to dual of L1, that is L1 dash. By definition of bounded functional, hence mod of f of EI less than or equal to norm of f into norm of EI less than or equal to norm of f, because norm of EI is equal to 1, we have written. F belongs to L1, we know this. So that the sequence f of EI, I is equal to 1 to infinity is bounded. Now we define a function t from L1 dash to k such that T of f is any element in L1 dash, that is dual space of L1 which contains bounded linear functionals. Image of f under T is equal to lambda I is equal to 1 to infinity. Give this equation number 3. T is well defined. We prove that T is linear 1 onto an isomorphism. So that by definition of dual that we have seen, it is proof that as T is a mapping from L1 dash to L infinity. In place of K, write here L infinity. L1 dash to L infinity, so that this L infinity will be the dual space of L1. So let us prove. To prove first, T is linear. For any elements f, g belongs to L1 dash. F and G are functionals, belongs to L1 dash, and alpha, beta belongs to K. Let f of ei is equal to lambda I and g of ei is equal to mu I. Ei are elements in basis. Each ei is a sequence. T of f is equal to lambda I is equal to 1 to infinity, and T of g is equal to mu I is equal to 1 to infinity. Consider T of alpha f plus beta into g is equal to alpha f plus beta into g into in bracket ei. T of alpha f plus beta g is equal to alpha into f of ei plus beta into g of ei. I is equal to 1 to infinity. is equal to alpha into lambda I plus beta into mu I is equal to 1 to infinity. Alpha into lambda I is equal to 1 to infinity plus beta into mu I is equal to 1 to infinity. Alpha T of f plus beta into T of g by definition of T of f and T of g. Hence, it is proof that T is linear. Now to prove T is 1, 1. To show that T is 1, 1, we show that kernel of T contains only 0 element. Let any element f belongs to kernel of T. Then image of f under T is equal to f of ei, I is equal to 1 to infinity, is equal to 0 element of L infinity. Because if f belongs to kernel of T, then image of f under T is equal to 0 element. Because image of any element in the kernel of T is equal to 0 by definition of kernel of T. So that as the sequence f of ei I is equal to 1 to infinity is equal to 0. So that f of ei is equal to 0 for each I. That is f of e1 is equal to f of e2 is equal to and so on is equal to 0. Now consider f of x is equal to f of summation I is equal to 1 to infinity alpha ei is equal to summation I is equal to 1 to infinity alpha into f of ei, because f is linear, bounded linear functional, because it belongs to L1 dash. Is equal to 0. Because f of ei is equal to 0. Hence f is 0 function, because for any element x, we have f of x is equal to 0. Hence kernel of T contains only 0 element. Hence T is 1, 1. Now we show that T is onto. We show that T is onto, that is every element in space L infinity is codomain, has its preimage in space L1 dash, because T is a function from L1 dash to L infinity. We are showing that L infinity is a range. Consider any element B is equal to mu I is equal to 1 to infinity. Be any element of L infinity. We show that it has a pre-image in L1 dash, where mu I belongs to K. Also, supremum of mod of mu I less than infinity. By definition, because sequence mu I, it belongs to L infinity, and L infinity is a space of all bounded sequences. So that for each element mu I, its absolute value is less than, it has a finite value less than some constant. So that supremum of mod of mu I is less than infinity. It will have a finite value. Because as every sequence in space L infinity is bounded, hence every element in every sequence, absolute value of every element in every sequence will be less than some constant k. Less than some constant. Here k is, we denote it for scalar field. So we can write less than infinity because it has finite value. So supremum of mod of mu I less than infinity. Now define G from L1 to K such that G of x is equal to summation I is equal to 1 to infinity alpha I mu I, where x is equal to summation I is equal to 1 to infinity alpha I ei. We have mod of g of x is equal to mod of summation I is equal to 1 to infinity alpha I mu I. This is less than or equal to summation I is equal to 1 to infinity mod of alpha I into mod of mu I. Less than or equal to supremum of mod of mu I into summation I is equal to 1 to infinity mod of alpha I. Less than or equal to supremum of mod of mu I, supremum over I, into norm of x, because norm of x is equal to summation I is equal to 1 to infinity mod of alpha I. This is less than infinity because supremum of mod of mu I is finite. We have seen. And norm of x, it is also finite. Hence, this value is less than infinity. Hence, mod of g of x is less than infinity. Hence, g is bounded. And now we show that g is linear. Since all of x is equal to summation alpha I ei, y is equal to summation beta I ei. G of alpha x plus beta y is equal to g of alpha into summation alpha I ei plus beta into summation beta I ei. Because x is equal to summation alpha I ei and y is equal to summation beta I ei is equal to g of summation in bracket alpha into alpha I plus beta into beta I into ei, whole into ei. This is equal to summation alpha into alpha I plus beta into beta I, bracket complete, into g of ei. Is equal to summation alpha into alpha I plus beta into beta I, bracket close, into mu I. is equal to alpha into summation alpha I mu I plus beta into summation beta I mu I is equal to alpha into g of x plus beta into g of y. Hence, G is bounded and linear. So, G belongs to L1 dash. Now, we see image of G under T. As G belongs to L1, so that T of G L1 dash, G belongs to L1 dash. So T of G is equal to G of EI. By definition of T, we define T as T of F is equal to lambda I is equal to 1 to infinity. And lambda I, where images of elements in basis under F. So T of G is equal to mu I is equal to 1 to infinity. So T of G is equal to B. We denote T of G by B. Hence, T is onto. We have taken an element mu I is equal to 1 to infinity in space L infinity and showed that it has a pre-image, and we showed that its pre-image is G. So image of G is mu I is equal to 1 to infinity. Hence, for any element B is equal to mu I is equal to 1 to infinity in L infinity space, we got an element G in L1 dash such that image of G under T is B. For any B in L infinity space, we got an element G in L1 dash such that T of G is equal to B. Hence, T is onto. Now it is proved that T is linear, T is 1, 1 and T is onto. Now we show that T is isomorphism. That is, T preserve the norm. That is, norm of any element in domain of T is equal to norm of image of that element in codomain, that is in range under T. That is, norm of TF is equal to norm of F. As T is onto, range is equal to codomain. Now we see the proof. Let any element X is equal to summation alpha I EI. It is EI and F belongs to L1 dash. F is a functional belongs to L1 dash, dual space of L1, where F of EI is equal to lambda I as we defined previously. Mod of F of X is equal to mod of summation I is equal to 1 to infinity alpha I EI. is equal to mod of summation I is equal to 1 to infinity alpha into f of ei, because f is linear, less than or equal to summation I is equal to 1 to infinity mod of alpha I into mod of f of ei. This is general property of mod. Less than or equal to summation I is equal to 1 to infinity mod of alpha I into mod of lambda I, because f of ei is equal to lambda I. Less than or equal to supremum over I mod of lambda I into norm of x. You can add one step again. Less than or equal to supremum over I mod of lambda I into summation I is equal to 1 to infinity mod of alpha I. In this summation, there is, for example, take alpha 1 lambda 1 plus alpha 2 lambda 2 plus alpha 3 lambda 3. If lambda 3 is greater than lambda 1 and lambda 2, then lambda 3 into alpha 1 plus lambda 3 into alpha 2 plus lambda 3 into alpha 3. This quantity will be greater than alpha 1 lambda 1 plus alpha 2 lambda 2 plus alpha 3 lambda 3. So that we can take supremum of mod of lambda I into summation I is equal to 1 to infinity mod of alpha I, where summation I is equal to 1 to infinity mod of alpha I is equal to norm of x. Give this equation number 5. Now, norm of f is equal to supremum over norm of x is equal to 1, supremum over x, where norm of x is equal to 1 mod of f of x. This is by definition of dual space. Norm of f is equal to supremum over x, where norm of x is equal to 1 of mod of f of x less than or equal to supremum of mod of alpha I. Supremum over I of mod of alpha I. This is by 5. Because mod of f of x is less than or equal to supremum over I mod of lambda I into norm of x. This is equation number 5. And from this we can write this equation. So norm of f is equal to supremum over I mod of lambda I. Is equal to norm of lambda I is equal to 1 to infinity. Norm of lambda I is equal to 1 to infinity. This is by definition of L infinity space. In L infinity space, the norm is defined in this way. That is supremum norm of any element lambda I is equal to 1 to infinity is equal to supremum over I mod of lambda I. This is the norm in case of L infinity space. So it is equal to norm of TF. We write here subscript as an infinity because this norm is in L infinity space. So norm of TF. This norm is on the space L infinity is equal to norm of F. And this norm on F is norm in L1 dash. In space dual space L1 dash. All of F belongs to L1 dash. Hence T preserve the norm. Therefore T from L1 dash to L infinity is 1 onto an isomorphism which preserve the norm. And hence dual of L1 space is L infinity by definition of dual that we have seen previously. Hence the theorem is proved. In next lecture, we see next theorem. Thank you.